So before we study gradient descent algorithm, let us learn a property on convex functions. Here in the graph I have, you can see a curve x minus 2 the whole square plus 3. You can also notice a point that corresponds to x is equal to 2. For this function f of x, point x is equal to 2 is a minima. As you can see that this is the place where the slope has its lowest value. So, gradient descent algorithm is a fundamental optimization algorithm used in machine learning to find minimum of a function. So there are many such applications in machine learning that we will look later on that requires us to find minimum of a function. So gradient descent is one such algorithm that helps us do that. Let us say we want to find minimum of a function. So our objective function will be minimum of f of x over x. Functions can be of two types. They can be convex, they can be non-convex. So difference between convex and non-convex function is that convex function only has one minimum point. So this function, there is only one minimum point. But a non-convex function will look something like this. So here, if you see within this region, this point is a minimum point. If you see within this region, this point is a minimum point. If you see within this region, this point is a minimum point. But overall, in the entire curve, this point is a minimum point. So these points are called local minima. But this point that is minimum across entire curve is called a global minima. So a property of convex function is that it only has one minimum point, which implies that the local minima is also my global minima. So keeping this property in mind, let us say if I have a curve like this and I want to determine where is my minimum point, then how will we do this? So as we all know, derivative of a function at a point will give us slope at that point. So when I am at my minimum point, and if I take derivative of this function at this point, it will give me slope. And always it is true for convex functions that if I take derivative of minimum point, the slope will be 0. So we can see this in this particular graph. In this graph at x is equal to 2, you can notice this red line, which is derivative of this function at this point, and my slope is equal to 0 at this point. But when we come to non-convex functions, the same property doesn't hold true, because let us say if I have this non-convex function, my derivative will be 0 at this particular minima. It will also be 0 at this minima. It will be 0 at this minima. So I cannot say for sure that in my non-convex functions, if I take derivative of this minimum point it is a local minima or a global minima. But if I have a convex function and if I take derivative of a point, I'll be sure that it has to be a global minima. So let us write a lemma. So say x star is the minimum point of my function, then if my function is convex, this is very important. If and only if it is convex, then it will be global minimum. So if I want to prove that a point is a minimum for a convex function, I will take derivative of the minimum point and it will be 0, where this x star is the minimum point. Also, every other point in the curve. So every other point in the curve, like all these points that are not my minimum point, for them my derivative will be greater than 0 for all x. For all x that is not x star. So keeping this property in mind, let us study gradient descent algorithm. So in gradient descent algorithm, our goal is to find minimum of a function f of x. And this algorithm is iterative in nature. We will see why. So let us say you are in a hill. You are in a hill and you are standing over here. So if I tell you to go to the minimum point of the hill, that is to come over here or here, will you go in this direction or in this direction? Yes, you will take this direction. So how did you determine that if you take this direction, you are going towards the minimum point? You decided this if the step you are taking in this direction is taking you closer to the minimum point. This is exactly what we do in gradient descent algorithm. The first step we do is we randomly select x0. So x0 is my initial point. So let us say if my graph was like this is a convex graph. So first I will select a random point. Let us say I selected this point and I will name this x0. This is the first step. Second step is to initialize two parameters. What are these two parameters? So first parameter is alpha. Alpha is my learning rate. We will talk about this later. And second point to initialize is d, and d is my direction. So imagine you are at x is equal to 0. If you go in this direction, you will never reach my minimum point. So you should know which direction to take. So if I take this direction, only then you can go to this particular point. And then the learning rate alpha is also known as step size. So let me explain you how this parameter helps us. Let us say I'm at x is equal to 0 and my step size is too large. That is, if I'm here, the next time I will go over here. Then I will miss my minimum point. So what I will do is, I will keep my step size small. So if I'm here, the next point I will go to is here. The next point I'll go to is here, and so on. I will reach this point. But if my step size was large, as I mentioned earlier, if I'm here, and if the next step I take is like I say over here, and then next will be over here somewhere. So I will never be able to reach my minimum point. So these are the two parameters that we need to take care of. So what we do is that we have a for loop. Since it is a iterative algorithm, we decide I equal to 1, 2, 3. For each step we decide what will be my alpha I and what will be my di. So the equation of gradient descent algorithm is for xi plus 1, that is where my next point will be, is determined by the previous point plus alpha I, that is the step size in the direction di. So let me explain this easily using an example. So let us say if we have a, also there is one more thing. There is a update rule. So update rule says that move in opposite direction of gradient. So what does this mean? Let us say if I have a function f of x is equal to x square and I initialized my x0 as 3. So what will be the next point I will go to? So as you know, this is how x square looks like, and right now I am at x is equal to 3. So what will be my next point? So how do we do this? So there are two parameters, as I said, alpha I and di. So alpha I usually in all practical purposes is kept very small. So in this case, let us say my alpha I is 0.001. This is a constant. I just declared this, and now di will be minus 1 times derivative of x of I minus 1. What do I mean by this? How did we get this equation? So what do we do is that since we want to go to a direction that takes me closer to the minimum, I would not want to go in this direction, correct? So if you take derivative of this function, let me show this to you using this example, that here we are at x is equal to 3. So what will be my f dash of x, that is f dash of 3? So derivative of x square is 2x, correct? So if I substitute value 3 over here, I will get 2 times 3, which is equal to 6. So 6 is greater than 3, that is 6 is higher than where we are right now. So where I want to go is, I want to go in negative direction, the opposite direction of my gradient. Hence, in this equation, we have a minus 1 term. Minus 1 term means it will take the opposite direction of the derivative. So my di will be minus 1 times 6, which is minus 6. Hence, my x1 will be x0 plus alpha 0 d0, which is, so x0 was 3 plus 0.001 times minus 6. So if you solve this, the answer will be 2.994. So my x1 is 2.994 and my x0 was 3. So as you can see that we went from 3 to 2.994, which is less than 3. And if we keep on doing this n number of times, we will reach the minimum point. So I want to help you visualize this using an example that I found from a website of UCLA. So here, this is a function that I showed you in the beginning of this video. We can declare a starting point. So let us say my starting point was 3. What will happen if my learning rate is too high? Let us say my learning rate is 1. So as you can see, This point is supposed to go to the local minimum over here, but what will happen in next iteration is that it will miss the minimum point because my learning rate is too high. We can also see this if I increase my learning rate further. This is my starting point and the learning rate is 5 right now. Then in my next iteration, as you can see, I have escaped the curve entirely. So what we need to take care of is to keep learning rate very small. But what will happen if my learning rate is too small? As you can see that right now I am at 0.3. In next calculation, I have just moved a little bit. It is so less that you can't even notice it moving further. This means if my learning rate is very small, I will have very small convergence, very slow convergence. So, we need a learning rate that is a sweet spot between these two. So, if my learning rate is 0.25, in next iteration, as you can see, I still haven't reached my minimum. So, let us go to second iteration, third, and so on. As you can see, as the iterations are increasing, my point is stabilizing and we are converging. And we have converged a very close number to 2. And 2 is my actual minimum. So this is how gradient descent algorithm works. We will study this in more detail in other lectures where other models use this algorithm to find minimum of a graph. There is also one more question that should come in your mind is that what will happen if this DI equation had +1 instead of -1? So the answer to that question is that we will be learning an algorithm that is gradient ascent algorithm. So there is also a algorithm gradient ascent. That means we want to find maximum in a curve. So if my di is +1 times derivative of the previous point, then I will be finding the maximum in the graph. So if di is -1, we have gradient descent algorithm, and if it is +1, I have ascent algorithm.